Hey guys, before we begin our lesson on polynomial functions, it's important to review imaginary numbers. Now you should have learned this previously in Algebra 2, but we need it for this lesson, so we're going to brush up on this. Now before we start, let's talk a little bit about imaginary numbers. Okay, they are considered non-real numbers, but I assure you, even though they are considered non-real numbers, they're very real. Their uses are very real. I is used in electrical engineering, it's used in differential equations, it's used in quantum physics, it's used in air traffic control. There are many uses for this number, even though it is called an imaginary number. It is a very important number. Okay, so now let's begin to evaluate these. I is the square root of -1, and that cannot be simplified, so that's it. I is the square root of -1. I squared is the square root of -1 squared. Okay, so squared and square root cancel, so I squared is -1. I cubed is the same as I times I squared. Okay, so we know that I squared is -1, so I'm going to replace this with -1, so it's I times -1, and that is -I. Or it could be written as the opposite of the square root of -1. I to the 4th power is I squared times I squared. I squared is -1. This I squared is also -1. -1 times -1 is 1, so I to the 4th power is 1.
Hey guys, today we're going to talk about polynomial functions. Specifically, we're actually going to talk about roots of polynomial functions. But before we get to the roots, there are some things about polynomial functions that we need to understand. First of all, the degree of a polynomial function. What is a degree of a one-variable equation? Notice this one only has x's, so it's a one-variable equation. The degree is the greatest exponent of the variable. Greatest exponent of the variable. In this case, that greatest exponent is 5. So this particular function has a degree of 5. The leading coefficient is just a number multiplied by the variable, so it is the number by the variable with the greatest exponent. Number by the variable with the greatest exponent. In this case, that number is -7. So the leading coefficient here is -7. A zero of a function and a root of an equation. We're going to lump these two together. And we're going to do that because they're basically the same thing. It's two terms for one thing. And what those really mean are they are the solutions of a function when it's set equal to 0. So when you set a function equal to 0, the zeros for the root of the equation are the same thing. And what it really means is where y equals 0. In other words, they are the x-intercepts. So here are some graphs. And we're going to talk about the maximum number of possible real roots. This right here is an example of a degree of 1. Y equals mx plus b, just x to the 1st power. And notice that it crosses the x-axis one time. The maximum number of real roots in this case is 1. If the degree is 2, notice it crosses the x-axis twice, it doesn't have to. If this is shifted up higher, it might not touch it at all, or maybe the vertex just touches, but we're talking about the maximum number of possible real roots. So a parabola like this, when it's shifted just right, can have as many as 2 real roots, where it crosses the x-axis twice. One like this, if it's shifted one way or the other, it doesn't have to touch 3 times, but the maximum number of times a graph like this can touch the x-axis, that's the real roots, is 3. You should notice a pattern going. When the degree is 1, it can cross 1 time. When the degree is 2, it can cross the x-axis 2 times. It doesn't have to, but it can. Degree of 3 can cross the x-axis 3 times. A degree of 4, again, if we shifted it up or down, it might not touch 4 times, but the maximum number of times it can touch the x-axis is 4. And if the degree is 5, like it was up here in this first equation, the maximum number of times it can possibly touch the x-axis is 5. So the maximum number of real roots is 5. Now, we're going to talk about real and imaginary numbers. So let's kind of go back and talk about our number system and the different types of numbers we have. The counting numbers, 1, 2, 3, and so on, those are called the natural numbers. Okay, so it's just the numbers that we normally count with. If we add to those natural numbers the number 0, now we've got the whole numbers. So it's 1, 2, 3, and so on, including 0. Then if we throw in negative numbers, so we've got 0, 1, 2, 3, and so on, and then also negative 1, negative 2, negative 3, those are called the integers. Okay, integers do not include fractions though, but if we throw fractions in with them, then we have all the rational numbers. Rational numbers are any numbers that can be turned into a fraction. The numbers 1, 2, 3, they can all be put over 1 and they're a fraction, right? But there are some numbers that can't be written as a fraction. Pi can't be written as a fraction. Any non-repeating, non-terminating decimal cannot be written as a fraction. Another word for a fraction is a ratio. So if it can be written as a ratio, it's rational. If it can't, it is irrational. So if we lump all the irrational and rational numbers together, we have all the real numbers. Real numbers are the kind of numbers that we tend to work with on a regular basis. There are also some numbers that we don't work with quite as often. Those are called imaginary numbers. The name does not mean they're just some made-up thing that doesn't have any application in the real world. Electrical engineers would use the imaginary number I. So they actually do have a real application in the real world. They're just called imaginary numbers. When we lump the imaginary numbers and the real numbers together, we get what's called the set of complex numbers. Roots can be real. In this case, we've got 2 real roots. However, if this was shifted up so that the vertex just touched that x-axis, we would have 1 real root. But there would still be another one. With degree 2, that means there still is another root. Or if it's shifted up like this, we have no real roots because it doesn't cross the x-axis at all. So we would have 2 imaginary roots. Okay, so here's a case where the vertex does not touch the x-axis and never touches the x-axis at all. So the number of real roots in this case is actually 0. In this case, we touch the x-axis twice, so the number of real roots is 2. This is the case where those graphs above are shifted so that it's not touching the x-axis the maximum number of times. Here's a degree of 4. The maximum number of real roots is 4, but it's shifted so that it only actually touches the x-axis 2 times. This one with a degree of 5 could have up to 5 intersections with the x-axis, but it doesn't. It has 3. So those are the real roots, which means the rest of the roots, the 2 roots missing here, are imaginary. The one missing here is imaginary. There's 2 imaginary ones here and 2 imaginary ones here. So whatever the degree is, that's the number of roots. Sometimes they're all real, sometimes they're not. But whatever the degree is, when the degree is n, it has n complex roots. Some of those may be real, some of those may be imaginary. But whatever the degree is, that's the number of roots total. All right, so let's talk about degree and leading coefficient. The degree is the highest variable of the exponent. In this case, that is 5. The leading coefficient is the number in front of that variable with the greatest exponent, that is -7. The greatest degree of the greatest exponent of the variable here is 3, so the degree is 3. The coefficient on that variable term is 1, so the leading coefficient is 1. Okay, so we've pretty well covered what we want to about polynomials. Now let's get into roots of polynomials. So here's a polynomial equation. It's set equal to 0. The degree is 3, which means it has 3 roots. They may all be real. There may be a mix of real and imaginary. The question is, are A, B, and C the roots of that equation? So here's how we find out. We evaluate f of 3. So that would be 3 cubed minus 3 times 3 squared minus 4 times 3 plus 12. If 3 really is a real root of this equation, then when x is 3, which is what we put in here, then y should be 0, because that would be an x-intercept. So 3 cubed is 27, minus 3 squared is 9, times 3 is 27. 4 times 3 is 12, so minus 12 plus 12. Now notice that 27 minus 27, those cancel each other out. Negative 12 plus 12, those cancel each other out, and we get 0. So when x is 3, y is 0, so that is an actual x-intercept. So the answer would be yes. 3 is a root of the equation. Then we'll try f of -2. -2 cubed minus 3 times -2 squared minus 4 times -2 plus 12. -2 cubed is -8. -2 squared is 4 times -3 is -12. -4 times -2 is 8. And then we have plus 12. -8 and +8 cancel. -12 and +12 cancel. When x is -2, y is 0. So -2, 0 is an x-intercept. So yes, -2 is also a root of that equation. Then we try f of 1. 1 cubed minus 3 times 1 squared minus 4 times 1 plus 12. 1 cubed is 1. 1 squared is 1 times -3 is -3. -4 times 1 is -4. And plus 12. Okay, these don't all cancel each other out. So 1 minus 3 is -2. Minus 4 is -6, plus 12 is +6. So the point 1, 6 is not a root. It's not an x-intercept. When x is 1, y is 6, not 0. So I would say no, 1 is not a root of the equation. Okay. Next, number 5. Here's a set of roots. there are 3 roots. Now, if there are 3 roots, that tells me that my equation is going to have a degree of 3. And in this case, what I have is 3 real roots. And I want to turn that into an equation. Now, if 2 is a root of the equation, and 3 is a root of the equation, and negative 4 is a root of the equation, if we go back to when we've factored equations in order to solve for x, we had something like that, usually equals 0. But here we've got 3 roots. Okay? Now, if the root is 2, then one of the 3 factors is going to be x minus 2. Because it's that 2 plugged in here, minus 2, that gives me a 0, times this equals 0. If 3 is a root, then x minus 3 is going to be a factor, because if I put a 3 here, I've got a 0, times these 2 factors equals 0. And then a negative 4 means x plus 4 is a factor, because if I put a negative 4 here, I get a 0, times this equals 0. So now I need to turn this into my equation. So I'm going to, it is an equation already because it's equals 0, but we're going to simplify this into a polynomial equation of the least degree. So x times x times negative 3, and negative 2 times x would combine to make negative 5x. And then negative 2 times negative 3 is plus 6. Okay, then we'll distribute all of these to all of these. So I've got x squared times x is x cubed. X squared times 4 is 4x squared. And negative 5x times x is negative 5x squared. Negative 5x times 4 is negative 20x. 6 times x is 6x. And 6 times 4 is 24. Okay, so there's my equation. Now I can just take this equation and combine all the like terms. So I've got 1x cubed. 4x squared minus 5x squared is negative 1x squared. Negative 20x plus 6x is negative 14x. And then I've got plus 24 equals 0. So for this equation right here, the 3 roots, the 3 real roots, the 3 places where it will cross the x-axis are at x equals 2, x equals 3, and x equals negative 4. Okay, we'll set up b similarly. X plus 2, x plus 3i, so we've got an imaginary number here, and x minus 3i. So this one has 1 real root and 2 imaginary roots, which means it only actually crosses the x-axis 1 time. So when you have 2 imaginary parts, I would deal with that first. So I'm going to leave that x plus 2 right where it is. I think it's just going to be easier if we deal with these first. If you want to deal with these 2 first, fine, but this is going to be easier. So I've got x times x, it's x squared. X times negative 3i is minus 3i times x, then plus 3i times x, and those actually just cancel each other out. Then I've got 3i times negative 3i, and that is negative 9 times I squared. Now let's simplify this I squared. So I is the square root of negative 1. Which means I squared is the square root of negative 1 squared, which cancels out that radical. So I squared is negative 1. So what this really means is negative 9 times negative 1. So I'm going to change that to x plus 2 times x squared, and then negative 9 times negative 1 is plus 9. Now let's simplify this. X times x squared is x cubed. Let's do this one next, just to keep the descending powers in order. 2 times x squared is 2x squared. X times 9 is 9x. And 2 times 9 is 18. So this equation right here has one place where it crosses the x-axis, and that's at x equals -2. The imaginary roots are -3i and 3i. You notice the degree is 3, so it has to have 3 roots. One of them is real, 2 is imaginary. Back in A, the degree is 3. It has 3 roots that happen all to be real. And then last, state the number of complex roots of each equation. The number of complex roots is the degree. This one has 3 roots. They may all be real, they may not, but it has 3 roots. Okay, then find the roots and graph the function. So we'll state the number of roots for both. This one's got a degree of 4, so it's going to have 4 roots. Next, we'll solve both of them to find the roots, and then last, we'll compare our solution to the graph. So here's what I can do to solve this. Both of these terms have an n in them, so I can actually factor an n out. N squared plus 4. So if this times this equals 0, then either this equals 0 or this equals 0. So the n is equal to 0. The n squared plus 4 we said equal to 0. The n equals 0, there's one of my solutions already. So for my final solutions, one of those roots is going to be 0. Solve this equation to find the other 2 solutions. We'll move this over here. So n squared equals -4. And then take the square root of both sides. Anytime you do a square root, your answer is going to be plus or minus. So n equals plus or minus the square root of -4. Now that -4, under a radical, I'm going to split that up. So it's going to equal plus or minus the square root of 4 times -1. The square root of -1 is I. So it's I times the square root of 4. The square root of 4 is 2. So plus or minus 2i. So my other roots are 2 imaginary roots, 2i and -2i. Well, like this, I can factor just as though it was c squared here and a c here, except when I factor it, instead of c and a c, it's going to be c squared and c squared. Now, what numbers multiply to make 7 and add up to -8? So those numbers would be -7 and -1. -7 times -1 is 7. -7 plus -1 is -8. So -7 minus 1. So I'm going to set this equal to 0 and set this equal to 0. C squared minus 7 equals 0. C squared minus 1 equals 0. So we'll move this over. C squared equals 7. And take the square root. C is plus or minus the square root of 7. Move that -1 over. C squared equals 1. Take the square root. C equals plus or minus the square root of 1, which is plus or minus 1. So our 4 roots. C is the square root of 7. The opposite of the square root of 7, 1, and -1. And then last, we're going to graph those so that we can compare our graph to our answer. So we'll clear out what we've got for y equals and then type in n cubed. I'm just going to use x cubed plus 4x. Graph. And we can see that it crosses the x-axis right here at 0. And that's the only time I see it cross the x-axis, so the other two are imaginary. And then clear that out, c to the fourth. I'm just going to use x again. Minus 8c squared plus 7. Graph. And I can see 4 real roots. Okay, so I've got one root at 1, one at -1, one at the square root of 7, one at the opposite of the square root of 7.